Hello, in this video we take a look at a Nobel Prize for Chemistry from the year 1903, won by Arrhenius for his electrolytic theory of dissociation. We'll see what it is a little later. First, some work information coming from the official Nobel Prize site. Here you see the link where it's coming from. Then some biographical information, work-related, summarized from the same site. And then finally, in this video, the award ceremony speech given to him, also retrieved and summarized from the Nobel Prize site, official site. Links are always at the bottom of the page, as you can see, if you want to see the original. Well, a connection between chemical and electrical phenomena became apparent in the 19th century, but it was unclear just what this relationship was. Svante Arrhenius studied how electrical current is conducted in chemical solutions. In 1883, he proposed a theory that when rock salt, which is the natural form of kitchen salt, natrium chloride, sodium chloride, which consists of sodium and chloride, is dissolved in water, it splits into sodium atoms with positive electric charges and chlorine atoms with negative charges. These electrically charged atoms, called ions, allow the solution to conduct electricity. And no electricity without moving charges. Here you see a schematical representation of what's happened. Here you have the sodium atom, which is dissolved in water, and you see it as a plus sign, and you see here around it water molecules which consists of two hydrogen atoms and an oxygen atom. Oxygen is negative, so it's attracted to the plus of the sodium, and the hydrogen atoms are positive, which are repelled by the also positive sodium ion. We can do the same for, if this was chlorine negative, then the position of the water molecules will be 180 degrees turned. Okay, some biographical information summarized. Here, Arrhenius began by assisting Edlund in his work on electromotive force measurements in spark discharges, but he soon moved to an interest of his own. This resulted in his thesis, Recherches sur la conductibilité galvanique, dus researches on galvanic conductibility from electrolytes, the in a sense, investigation on the galvanic conductivity of electrolytes. From his results, the author concluded that electrolytes, when dissolved in water, become to varying degrees split or dissociated in electrical opposite and positive charges, ions. We saw it with the sodium and the chloride just before. The degree to which this dissociation occurs depended above all the nature of the substance and its concentration in the solution. Being more developed, the greater the dilution. The ions were supposed to be the carriers of the electrical currents, for instance in electrolysis, but also of the chemical activity. The relation between the actual numbers of ions and the number at great dilution, when all the molecules are dissociated, give a quantity of special interest, the so-called activity constant. The idea of a connection between electricity and chemical affinity, once advocated by Berzelius, had, however, so completely vanished from the general consciousness of scientists that the value of Arrhenius' publication was not well understood by the science faculty at Uppsala, where the dissociation took place. On the other hand, Otto Pedersen, professor of chemistry at Stockholm's Högskola High School, I think, probably university, emphasized the originality of this dissertation, and William Ostwald traveled to Uppsala to make the acquaintance of the young author. The fundamental importance of Arrhenius' work was thus made clear, and at the end of 1884 he got a docentship at Uppsala in physical chemistry, the first in Sweden in this new branch of science. Through Edlund's influence, he was awarded a traveling fellowship from the Academy of Sciences, which enabled him to work in 1886 with Oswald in Riga and with Koolruis in Würzburg. In 1887 he was with Boltzmann in Graz, and in 1888 he worked with Van Hoff in Amsterdam. Big names all, of course. Here you can see the same what we just saw. And, here is added in that the chlorium ion, which is negative, and you see here's this positive sodium, and you see that what I just told, the hydrogen part of the water molecule is positive and attracted by the chlorine, while the negative part, the oxygen, is repelled by the chloride. And in the sodium, it's just the other way around, as you can see, because sodium has a positive charge and chlorine a negative one. This is the serialization of ordinary salt in water. During these years, Arrhenius was able to prove the influence of the electrolytic dissociation on osmotic pressure, the lowering of the freezing point and the increase of the boiling points of solution containing electrolytes. Later on, he studied the importance in connection with biological problems such as the relationship between toxins and antitoxins. Chemotherapy, first Nobel Prize in Medicine in 1991 was awarded for that to Behring. Its role for digestion and absorption as well as for the gastric and pancreatic juices. The paramount importance of the electrodissociation theory is today universally acknowledged, even if certain modifications have been found necessary. In 1891, Arrhenius declined a professorship offered him from Gießen, Germany, and soon afterwards he obtained a lectureship in physics at Stockholm's Högskola. In 1895 he became the professor of physics there. Here, in addition, rector from 1897 to 1905, when he retired from the professorship. He got an invitation to a professorship in Berlin, and the Academy of Sciences then decided in 1905 to start a Nobel Institute for Physical Chemistry with Arrhenius as its chief. Initially, he had to work in a rented flat, but the new building was inaugurated in 1909. A large number of came to him from Sweden and from other countries and helped him to give. I hesitate by the currency. I think that students has to be on this place. In 1900, Arrhenius published his letter in this difficult. It is a teaching book on electrochemical theory. It is probably Swedish. I'm not able to speak that. And in 1906 followed Theories of Chemistry, this is German, and Immunochemistry. And in 1918, the Silliman Lectures series on solutions. He took a lively interest in various branches of physics, as illustrated by his theory of the importance of the carbon dioxide content of the atmosphere for the climate. We'll come back to that later. His discussion of the possibility that radiation pressure might enable the spreading of living spores through the universe, panspermia, and his various contributions to our knowledge of the Northern Lights, Aurora Borealis. In 1903 appeared his teaching book on cosmic physics. Oh, here it is. Here you see an electrolytic cell, which is of course used to get electricity from dissolved ions. Then the award-winning ceremony speech by Dr. Turneblad. During the first year of the last century, Volta made this first electric pile. We saw a modern version just a slide ago. By studying the chemical action of the electric currents thus obtained, Davy in Britain and Berzelius and Isingen in Sweden, and they arrived at the conclusion that the relationship between electrical and chemical phenomena was one of cause and effect. On the basis of this idea, Berzelius established his well-known electrochemical theory, which reigned supreme until the middle of the century. That's the 19th century. However, new discoveries showed that this theory would not stand up to examination, and chemical phenomena ceased to be explained as being due to electricity. It was generally accepted that these chemical changes of matter were due to a certain affinity, though the origins of this affinity was absolutely unknown. Then came the heyday of thermochemistry, when it was believed that the explanation of the transformation of chemical energy during chemical reactions lay in the heat phenomena occurring during chemical processes. Around 1880, Svante Arrhenius, then studying for a doctorate in science, arrived as a result of researches into the movement of electrical currents through solutions at a new explanation of the causes of chemical phenomena. For instance, he attributed them to the electrical charges contained in the constituent of reacting substances. Electricity was induced, this means in other words, by the way, introduced as a decisive factor into the theory of chemistry. In other words, the basic notions of the theory of Berzelius had come back into favor, although in a greatly modified form. In the time of Berzelius, this notion rested on a qualitative basis only, whereas Arrhenius' theory determined it quantitatively, thus allowing it to be treated mathematically. That's a big step forward, of course. In his doctor's thesis 20 years ago, now much longer ago, of course, Arrhenius had deducted from the principle all known laws governing chemical changes. But despite this new theory, very little was understood. It conflicted with current ideas as to prove them. Here you see again an electrolytic cell in which chlorine and sodium are dissolved. Here you see the chemical reaction which I added, by the way. You see sodium chloride comes in and water comes in and it's dissolved. And sodium hydroxide, hydrogen and chlorine come out of it. All in the molecular form, of course. According to this theory, for instance, common salt, sodium chloride, when dissolved into water, splits up in varying extent. In other words, it is dissociated into its constituent parts, which are diametrically opposed but charged with electricity, into ions of chlorine and sodium, the only chemically effective substances in a sodium solution of common salt. The theory also claimed that when an acid and a base react on a panel, water is primarily conduct and salt the secondary and not reversely, as was then generally believed. Ideas so contrary to those current at the time could not be accepted immediately. A struggle lasting for more than 10 years and an enormous number of new experiments were required before the new theory was accepted by everyone. During this long battle over Arrhenius' theory of dissociation, tremendous advances were made in chemistry, and ever closer links were established between chemistry and physics, to the great benefit of both sciences. One of the most important consequences of Arrhenius' theory was the completion of the great generalization for which the first Nobel Prize for Chemistry was awarded to Van 't Hoff. Without the support of Arrhenius' theory, that of Van 't Hoff would never have gained general recognition. The names of Arrhenius and Van 't Hoff will go down in history as making the modern period of the science, and for this reason that the Academy, despite the fact that the experimental basis of the theory of dissociation belongs to physics, did not hesitate to award Nobel Prize for Chemistry to Arrhenius. The Academy of Science counted itself fortunate in being able to award the Nobel Prize for Chemistry this year to the compatriot Berzelius, who rehabilitated fundamental notions of his theory, and the task is made even more pleasant by the fact that the choice is supported by the most outstanding scientific authorities of our day. The world of science already recognizes the importance and value of your theory, but its luster will continue to increase in the days to come as yourself and others use it in advanced the science of chemistry. Physical research has contributed to your discovery, and this fact throws new light on the relationships, more sense than proved, between the different natural science, the common objective of which is to solve the riddles of life. Success spurs us on to new endeavors. May your future work bear even more abundant fruit. And when championed of the spirit of learning advance along the trail that you have blazed, may we remember in the proud words, il fecit, that is Latin, and it probably means something like, he has done it. And here you see, I always said that it would come, that Arrhenius very early, around 1900, warned for the detrimental warming of the earth caused by burning coal and gas and oil and that sort of things. If you want to read it, you can better stop the video. Last, there will be another video on the Nobel Prize lecture held by Arrhenius in 1903. As said, this will be another video. Thank you for watching. Maybe till another time.